in a way.
Okay, is my screen visible to all of you?
Yes, sir.
Yes, sir.
Good.
Yes, sir.
Okay, so now we are doing analysis of the sine triangle PWM. We have understood a lot of things now. So what we are trying to do, we are trying to come up with the ripple current on basis of what switching frequency we have, what modulating signals are. On basis of that, we are trying to understand how can we have an estimate of the current ripple coming in the system. So this is what we are going. If we need to know the current ripple, we need to know the voltage ripple that is being fed into the system, because the inverter voltage, which is having two components, one fundamental and another the ripple current, ripple component. So each one is responsible for its own current. For example, fundamental voltage is responsible for fundamental current and ripple voltage is responsible for ripple current. This understanding we have, right?
Yes, sir.
Okay. And because we are talking about linear system, so if we have to say that what is the total current flowing into the system, it is basically sum of these two, the ripple current plus the fundamental component. So we can solve these two separately and we can come up with the actual current, which may look like this: fundamental superimposed with the ripple. So there will be a band of ripple which will be sitting on the fundamental component. Correct? So we have drawn the equivalent model, or you can say per phase equivalent circuit for the fundamental and the harmonic separately. Why it is different? Because on the back EMF side or on the grid side, we assume that there are no harmonics. For simplicity we are doing, and generally it is true also. Compared to what harmonics we are injecting from the converter, we don't have so much harmonics on the grid or back EMF side. And because we are having PWM voltage which is switching between plus VDC by 2 and minus VDC by 2, and here we have nice sinusoidal voltage, so we need to have some reactive element in between to match these two voltages. So you may assume like this is kind of a current source element and this is kind of a voltage source element. So this is how we are having. The reason for having inductor is that we are trying to match two different voltages. Correct? So if you don't have anything directly, this plus VDC by 2 will be shorted with whatever voltage is on the other side, or minus VDC by 2 getting shorted with the other side. So we need to have a reactive element. Now, when we are trying to have that, the fundamental model or fundamental component model will see the grid voltage or back EMF as this EMF on the other side. Whereas the harmonic component would not see any voltage coming on the other side, on the grid side. So we will have two different equivalent circuits, one for the fundamental, another for the ripple component. And this is used here for computing the ripple component of whatever sine triangle PWM we are having. This thing will be used everywhere. This model is true for harmonic, individual harmonic component. Let's say you talk about 5th, 7th or 11th, 13th and so on, or combination of all the harmonic components, which is called as ripple. So reason for having ripple in the current is because we are feeding ripple in the voltage. Someone asks a simple question: why do we have ripple in the PWM based system or voltage source inverter based system? Because we are feeding voltage ripple. The other way to see is that we are feeding some error in the voltage compared to what we need to feed actually. So the most important thing to compute for the computation of current ripple is how much error voltage you are feeding into the system. And because we are dealing with the PWM voltage based system, the pole voltages may have some common mode. So which is why pole voltage alone cannot decide what the ripple current will come. It has to be decided on basis of the line to neutral current component, the voltage component. So which is why we need to derive our VRN, line to neutral voltage, from the VRO, VYU, VBU. And this is what we have done over here. We have got the VRN corresponding to this position of the subcycle and position of these modulating signals. So assumption we have made that the frequency of this triangular carrier is much higher compared to the fundamental frequency. So within one switching cycle, within one switching sub-cycle, TSW by 2, the change in the modulating signal is not much. It's almost a constant value during this. Marginal change or almost no change. So this is the basis of our computation. And now what we have done, we have got the pole voltages, and from here we have computed our VRL. This is always true, whether you go for 6-step or you go for sine triangle or any other PWM technique, this is always true. Now, once we have the VRN, we are trying to realize the average value of VR, which is same as average value of the pole voltage, and which is actually equal to M times of VDC by 2. So we have taken this MR as 0.2. So average value of VRO, which is shown here, is 0.1 VDC. And this is same as what average value VRN would contain, because these two are different only in terms of common mode, not in terms of fundamental. So the value which is realized here for the fundamental component is true here as well. And that is why we are able to subtract now this value to get the VRN ripple or VRN error. So this is what the blue waveform, maybe I'll draw once again, little bit darker. This blue waveform, what you are seeing here, is basically the ripple voltage or error voltage. When I say ripple voltage, the average value of this voltage, what you are feeding in the system, is 0. You have subtracted the average value. So whatever is remaining is only the ripple, or you can say error into the system. And because this has no average value, so the current which it will generate, that also cannot have any average value. We are talking about a linear system. So which is why the ripple current can be drawn corresponding to this voltage on basis of this equivalent model what we have discussed earlier here. So what it is having, basically simple inductance is there, and because these voltage levels are DC, so the current ripple looks like a linear set of linear wave, this you can say set of lines. Okay, we are not approximating anything over here. So which is why the ripple what you see is mostly looks like a triangular ripple. The reason being this, we are talking about voltage levels which are like kind of DC, and we have only inductive element over there. So almost linear current we see in every zone. The only thing what we need to keep in mind is that when we are starting from 0, we must end up at 0. And this assumption is true as long as your switching frequency is, say, larger than your fundamental frequency, and the boundary can be 21. Sometimes this may be true for 15 as well, but as you start going below 21, you may start seeing some difference. Some slight difference could be there. Correct? And as you go close to say 9 or 5 or 7, basically if you start from 0, you will not end up at 0, which means actually the current is not starting and ending at 0, but at some other value. The only thing which is true in all the cases is that it cannot have any DC value. So we need to adjust the waveform such that the DC value is removed, and which will result into something. So if I talk about say pulse number 9, so it may look like somewhere here it is starting, and on 9 or 5 you can say it would be better, and then it can go like this. So it will start and end up at the same point, but the starting point, ending point may not be 0. Average value may be 0. Average value will be 0 because there is no average voltage applied here. You understand the difference? When we are doing computation for high pulse number, we will very well we will see that it is starting from 0 and it is going to 0. If you do same thing for 7 or 5 or 9, you may see that it is not exactly starting from 0, but it is going somewhere else. but average value still would be 0. So this computation is correct for whatever pulse number you do, but only thing you need to keep in mind, if your pulse number is very low, then it may not have the starting point at 0. We will see that shortly. So now what I'm having, let us say, this is the way we are computing different current levels. So these current levels, say I1, then I2, then I3, and then I4. So I4 is also going to be finally 0 if we have sufficient pulse number, say 21 or 33 and so on. And this current will rise to I1, then again go to I2, come back to I3 and come back to 0. Like that it will go in linear fashion. So the important elements what we need to know for this computation is what is the DC bus voltage, then what is the leakage inductance, and then most importantly what is the duration of this. Of course, DC bus voltage, you can say the combined voltage. What is the voltage coming across this inductive element? The combined voltage you can say. Then the inductance and then the time period. These three things you must know before computing this. Now time intervals, we have seen that very easy way to compute is you go by similar triangle method. So if you take one segments of this, so this green triangle you can take that is similar to the biggest triangle over here. Then you take the blue, again put it similar to the biggest, then take the black one and make it similar to the biggest one. And this is how you can compute the different intervals T1, T2, T3, T4 and so on. So T4 is basically whatever is remaining from Ts by 2 is T4. Or you can just see from here how much it is coming. You understand my point? Clear, right? There is no confusion in this.
Yes, sir.
Now once we have computed, so what we can do, we can identify the place where we are going to have worst ripple. So worst ripple means, worst current ripple means the place where we are having worst voltage ripple. And where we will encounter worst voltage ripple, wherever we are not feeding any actual voltage, but still we are applying PWM. That means at the zero crossing of R phase voltage.
Sir, sir, I have a question regarding yesterday's analysis. Sir,
Yes.
sir, the question that you give is when we consider carrier amplitude 1, then the ripple coming out to be is 3.048, and when we consider is it equal to zero point 0.8, that is similar to the m value that you give, then it comes 3.81. So sir, value increases ripple, but zero point 0.8 is better, so why it is not getting a lesser value as compared to 1?
What are you changing?
Sir, carrier amplitude.
Why are you changing carrier amplitude?
So to get better waveform, zero point 0.8 carrier amplitude, if we consider zero point 0.8 in modulating signal, then
Better you consider 0. Why 0.8? So you don't understand, right? This, when we say we are having the amplitude between plus and minus 1, what is the reason behind that? Our modulation index is changing within these values with respect to these values. You understand my point?
yes
So
sir.
your time intervals for which you are applying V plus VDC by 2 and minus VDC by 2 are seen how much is this value relative to your modulating signal. If you make modulating signal 0.4, it is assumed that this is 1 and minus 1. You cannot say, oh, I had only 0.6 here and minus 0.6 here. This is not related, right? 0.4 means it is 40% of the peak value.
Yes, sir, sir. But in yesterday case, you told that consider peak to be 0.8. Capital
That
M, capital M value 0.8.
is this capital M value?
No, sir, it is a small m. But
Is this a small m?
yes, sir, MR, M sin omega t.
This is carrier, right?
Yes, sir, this is carriers.
Where is m in this?
Sir, I'm saying that in yesterday's case, you told that consider instead of one capital M value to be 0.8.
So capital M value I'm saying, where am I asking you to change this carrier peak? What is capital M?
Sir, modulating signal amplitude.
Is this modulating signal?
No, sir.
Why are you changing this? See, meaning is that you are having motor to control. So motor to control, you will have by default V by F in most of the cases. You have sinusoidal modulating signal. Now it is not necessary that this sinusoidal component will have same peak value always, right? It will be somewhere here, sometimes somewhere here, of course. Frequency will also change. Sometimes it may be here, but whatever we are doing, we are keeping it within the boundary. What is the boundary? +1 and -1. This is our carrier boundary. Why are you changing this? Capital M is related to this peak. What is capital M?
Sir, if we, yes, sir.
Say.
Sir, if we have capital M zero point 0.8, then if we consider zero point 0.8 carrier value also, then we get better
Why would
response.
you, if you have M equal to 0.8 and carrier peak also 0.8, modulation index is it 0.8?
No, sir.
Why are you changing the carrier? I am surprised. Who asked you to change the carrier peak? You understand the meaning of 0.8? What it means? The peak is 80% of the carrier. That's the meaning of 0.8. Now, if you bring this down to 8.8, what happens?
Then, sir, we ignore the 20% of upper half.
If you put it like this, then actually your modulation index is 100% of the carrier. What you are ignoring? Sampan, you are thoroughly confused. I don't know why. Anyone else having this doubt? This is only relative value with respect to carrier. Say I am having my modulation index at 0.4. What is meaning of this? The meaning is my modulating signal is 40% of the carrier peak. I am not disturbing the carrier peak at all. I cannot. If I disturb, this meaning will go away. Where did you see this carrier changing? Sampan?
Sir, as in the last case, we are considering MR, MY, small MR, MR, MY values. Then
Yes.
there we consider capital M1. So, so if we see, sir, at MR, small MR value equal to be 1, then we get the positive pulse for the whole cycle.
Yeah, so
But if we consider capital M value equal to zero point 0.8 and make the carrier to be remain to be at 1, then sir, we definitely get some negative pulse also. But if we consider it carrier amplitude to zero point 0.8, then we get the same kind of scenario that we discussed.
Are you listening to what you are saying? Are you listening to yourself? What is meaning of percentage, Sampan?
Sir, sir,
What
what?
is meaning of percentage?
Sir,
What is meaning
relate,
of percentage?
sir, relative to the total value, what
Hmm. When
portion
I
we.
say 40%, what is the meaning of this? What is meaning of 40%? 40% of the total, right?
Yes, sir.
Then if you say your modulation index is 0.8, which means 80% of the total, 0 to peak, then can you say that your total is also 0.8?
No, sir.
Why are you changing this? I'm not understanding. Who asked you?
Sir, I do the analysis with 1 and also at point 8.
What is 0.8? What is 0.8?
Sir, carrier amplitude, I consider.
Why are you changing that? My basic question is that. See, of course, if this is plus 1, minus 1, you are having your modulating signal here. You will get some VRO at plus VDC by 2 and minus VDC by 2. Okay, corresponding to this, you will get some this much plus VDC minus VDC by 2, like that you will get. Of course, if you bring down your carrier here, what will happen?
Yes, sir.
Now, what will happen? Tell me, if you bring down your carrier here,
Sir, now now we will get the positive pulse for the full all the
can
time.
you bring it down from here to here? What is meaning of modulating signal and carrier in this case?
Yes, sir.
If this is not intersecting at all, what it is doing there? Why is there carrier?
Yes, sir.
Why are you changing these values? I am still surprised, shocked actually. Who asked you to change? Of course, if you change, you will get because your relative value is changing. Relative value between the modulating signal and this is changing. So of course you will get wider pulse. What is the problem in that? What's the problem? You bring down your carrier to 0. You say, okay, I'm always getting plus VDC by 2, irrespective of my any modulating signal. Of course you will get.
Yes, sir. Sir, I
That's
check
why,
the. Yes.
no, that's why I asked, why not 0 carrier? Why 0.8? Make your carrier 0. It is always plus VDC by 2. Solved.
Yes, sir.
Anyone else trying to change the carrier amplitude? And then you justify also. Do you not think what you are doing? If you bring down these levels below, for the same thing, you will have intersection at larger, at bigger interval. And so this pulse will be bigger. What's surprising in that?
Sir, but here we consider small MR values. But
What we
I'm
need to consider actually,
sir, as we go along the modulating signal, then the small m value rises from -1 to 1, and it follows the same cycle. But if we changes the capital M, sir, I am actually not actually. I think I am not understanding.
my God, I am about to finish sine triangle and you are confused between what is plus m and what is minus m, is it? Or
No, sir.
what is carrier, how the sinusoidal, this thing is changing?
No, sir, I am getting all these things, but capital M value and small m value.
Huh. Yes, yes, please carry on. I need to listen to this actually.
Sir,
Yes, yes, please go on.
sir, if we consider capital M equal to zero point 0.8, then MR we get zero point 0.8 sine omega t. So
Hmm.
it vary from minus zero point 0.8 to zero point 0.8. That's why I changed the carrier value.
I'm not getting someone. What is the confusion in this? Of course, it will change from minus zero point 0.8 to plus zero point 0.8. So what's the problem?
Sir, that's why I changed the carrier
Why
to
you
get.
need to change the carrier if it is changing from minus zero point 0.8 to plus zero point 0.8?
Sir, just to get the analysis of with one and point it. Sir, there I noticed that the ripple in the current value increases in case of zero point 0.8 when we consider carrier amplitude to be zero point 0.8.
You again listen to what you are saying, Sampan. You are talking about something very, very absurd. Is it always necessary? See, this is the sinusoidal modulating signal I am having, right?
Yes, sir.
What is the equation for this?
So it is 0.75 sine omega t.
Okay. Some capital M sin omega t, where capital M value is zero point 0.7, let us say. Is this not valid sum triangle PWM?
Yes, sir, it is valid, sir.
So, why you need to choose the carrier, I am asking.
Sir, if we change it to zero point 0.7, then it is not getting
My God. Sampan, what is the meaning of zero point 0.7? Meaning
the
of
70
7 is only
70%.
70% of this height. Then if you change it to zero point 0.7, what it will become? Will it remain 0.7?
No, sir. Yes, sir. Now I understand you, sir.
Why are you changing carrier? I'm not asking. Who else is changing the carrier peak value?
Sir, it is zero point 0.7 is it with respect to the carrier. So if we get the carrier to zero point 0.7, then it becomes 100%. So there is no meaning in changing. So now I get it, sir.
Thank you. Don't ever dare to say that I'm changing the carrier amplitude unless some very special requirement is there.
Yes, sir.
I don't know from where you are getting all these ideas. Who asked you to change it? Can I not have modulation index value zero point 0.1 for this carrier? Can I not have zero point 0.1 for this? What is the problem? I can have something like this.
Yes, sir. Sir, I, sir, I go into the mathematical, but the forget the basic that why we are getting it, and just do.
Okay, wanted to show some things in MATLAB. Let us see how it goes. So here I am having, let's say, a 50 hertz system, which I am trying to run at 40 hertz. So obviously my modulation index will be, no, if we keep V by F, it will be 0.8. So for this, I'm trying to have some carrier which is having 33 times of the fundamental frequency. So carrier having frequency 33 times of that. So pulse number is 33 over here. And something like 700 volts of DC bus and this kind of leakage of 2 millihenry, something what I told yesterday. So for this actually, if we try to see how the current and other things are coming, so we can see one by one how these things are coming up. First of all, this is how my modulating signal and carrier would look like. Okay, let me clarify again. If I have to run the system with only 20 hertz frequency, then my modulation index will actually change. It will look like this. It has reduced. 20 Hertz means it has come down to 0.4. You understand my point? So if you are going in V by F mode, gradually your modulating signal will increase from 0 all the way up to 1 peak value. Understand my point? Okay. Now, if you have got that understanding, let us try to see how the pole voltage is coming. What we have seen, basically the width is changing, going on increasing and then coming back to 0. So let me have a reasonable amplitude so that it is visible little bit, say 0.8. Here. So what I will do, I will remove some of the things, say VRN I will remove, and then I can remove the carrier, or okay, let it be there. So this will help in understanding. Fine. So here let us analyze only up to from 90 to 180, let us say. This is my peak value, or maybe I will make it 75. So that is better. See here, somewhere around this 90, this is kind of having the peak value. So we can see this subcycle over here. For this subcycle, what we have, because this is falling down, so we have first the minus VDC by 2 and then the plus VDC by 2 interval. So this plus VDC by 2 interval is biggest over here, and gradually you see that it is reducing all the way, and let me write 190 over here. So this is here, it is crossing the 0. So this becomes equal. Understanding my point? So all the way from the highest, so if you go a little bit on the lower side, you see that this pulse width is increasing. It has become maximum somewhere here, and then it is gradually reducing and coming down to equal, plus VDC by 2 and minus VDC by 2. This is how we are realizing the voltages, average voltage in the pole voltage. So now if you go up to, let us say 270, or let me write 300, so then again you see that the positive pulse width has reduced to a very low value, close to 270. This is around 270. The positive width is very, very small. The negative has increased. Correct? This is the meaning of pulse width modulation. You can see the variation, the gradual change in the positive pulse width or negative pulse width, whichever is comfortable for you. It is gradually increasing up to the positive peak. So I can go to 0. See, here it was equal, going up to maximum, coming back to equal, and then reducing gradually to a very small notch near 270 degree. And again, it will come back to almost equal interval here. This understanding you are getting? Correct? It is happening at every subcycle. This change is occurring at every subcycle. This is what we understand from the good waveform of VR. Now, if I plot, say VRN, so I will remove, let's say VRO. So you can see here straight away the violet waveform, what is shown over here is basically the VRN. This is not having the voltage levels of plus VDC by 2 and minus VDC by 2. It is what we have seen somewhat in our analysis, right? So something like VDC by 3, 2 VDC by 3, then VDC by 3, minus VDC by 3 and minus 2 VDC by 3. These kind of voltage levels it is assuming. So same analysis what you have done for 0.2 value of modulation index, which means you are dealing with somewhere here in this zone, which is close to the 0, somewhere around 0.2. Now if you increase this and go up to the near the peak 0.8, you will see a new voltage level coming over there. which will be 2 VDC by 3. Okay, if I zoom this section, see here, so near 90, what we are seeing that there is voltage level corresponding to 2 VDC by 3, VDC by 3 and 0. And as you come down in the modulation index, lower values, somewhere you may see only VDC by 3 and 0, which is what we have seen in our case, right? So for lower value of modulation index or lower value of your, wherever you are doing analysis, if that corresponds to lower value of M, then you may not see all the voltage levels. It is only for the higher modulation index or close to the peak of the fundamental, you will see another voltage level coming up. You understand my point? So basically more voltage is required for realization of this average value. That's why it is coming like that. Here during this only VDC by 3 and 0 are sufficient. Sometimes it may have a small notch which is like going for 2 VDC by 3. We can ignore that sometimes. It's a very fine notch. Correct? So the analysis will be confined to plus VDC by 3, 0, plus VDC by 3, and then minus VDC by 3 and 0. Like that it will have the voltage levels. So understand the difference. Same thing what you have done for, let us say, a small MR value equal to 0.2. If you try to do the same thing for a small MR value equal to 0.8, then you will have these voltage levels as well in the analysis. Understanding my point? Okay, now let us see what other things we have. Okay, this I have tried to plot the ripple. So I should have basically the fundamental voltage component as well, but it may not be visible. Okay, somehow you can identify, right, this 0 to 360, how it is going. So where can we expect? And this is almost no load operation. So our current, okay, maybe that plot would be better. This and this. So ignore these components. These are some transformations. Yeah. Now, here you see that we have three-phase current coming. So R, Y, B, all three are coming, right? So because this is plotted with respect to its own 0 degree, so that's why it is coming looking like in phase, but actually this is almost 90 degree. You see the ripple, how it is going and increasing here and then coming gradually to a lower value and then going in a sinusoidal manner. This is what I was suggesting earlier. Same thing I have plotted here separately for the ripple. So it has too many components. First thing is your error voltage, what we have seen corresponding to the VRN. So let me show it one by one. Okay, let us say from 0 to 100 we can have, and let's have only the voltage error component in this as of now. Okay, there are two things over there. Just let me check what is the other one. Okay, fine. So this may be the actual voltage what is coming over there, and then the subtracted, this slanting line is basically the kind of ripple what we are having. Anyway, so I can remove this part. Kind of, this is the error what you are going to see. So this is what we have observed in our analysis also. Let's say you take one subcycle, this is how the plus minus VDC by 3 and all these levels may come up. Now corresponding to this, we are generating our current ripple. So what we will have, let's just plot this one only. And let's get rid of some of the things. Yes, here. Now each and every subcycle you see that it is having this kind of ripple what you have tried to compute. Correct? This is close to somewhere we are changing from 0 degree all the way up to 90 degree and so on. So one subcycle also, if you try to see, it may look like something like what is seen over here. This is one subcycle. So current may be going, then changing all these things. So this is what we may observe. You understand my point? Basic nature is that when you have, let's say, going from 0 to 360, you will see that ripple is gradually reducing and then increasing. And these places where you see the maximum ripple, that corresponds to what I told, the zero value of the voltage. Understand my point? This is coming at 90 degree of the current because this is 90 degree lagging. So here is where we have the crossing, zero crossing for the voltage. This is where we have zero crossing for the voltage. That's why this is appearing at the peak of the current. You understand my point?
Sir.
Yes.
Yes.
Now the last thing which I wanted to say in this, there were a few more things, but then when you are having your carrier and trying to do analysis for the zero value, MR equal to 0, you may have MY, MB corresponding to what modulation index you are having. Now again, understand, when I say that you have to do analysis for the system where M could be say 0.8, then the another thing which you need to know that at what theta we are doing this analysis. So for zero crossing, of course, we have only two options, theta 0 degree or 180 degree. So corresponding MY and MB values are now fixed. So any of these information are sufficient to tell that what values of MR, MY, MB I am asking for. If I ask you to do analysis at theta equal to some 30 degree, then you know what MR, MY, MB I am asking for because this I have stated. Or I may say that the motor is running at 40 Hertz, 50 Hertz rated motor is running at 40 Hertz, which means what? V by F has to be maintained. So that means my modulation index is basically 80% of the full value. You understand this point? So either way, the information may be given either in terms of frequency or in terms of the direct modulation index value and including the angle, or directly I may give this at MR, MY, MB, these are the values, compute what is the current ripple. So practice for all these things. Okay, how to correlate this with modulation index and then modulation index with theta and then the values of MR, MY, MB. Now what I'm trying to say over here is that when you are doing this zero crossing analysis and you are finding ripple going on one side, actually the other part we have not seen. So peak to peak ripple, why I say it is maximum, because corresponding to this, say this is extended here, corresponding to this half subcycle, the first half which you have done the analysis, voltage levels, what we will find is basically it is changing here and it is changing here and changing here. Correct? So it will be 0, then plus VDC by 3 and then going minus VDC by 3 and then it is going to 0. And here the scenario will be inverted. The value will be inverted. It will first go to minus VDC by 3 here. Sorry. Yes, it will remain minus VDC by 3 and then plus VDC by 3 and then coming to 0 up to this. Reason being, MR is less than the carrier throughout this duration. So it can have only minus VDC3 values between this interval. Only when the MR value is more than carrier, we can have plus VDC by 3. That's why outside this zone, this is coming plus VDC by 3, internally it is minus VDC by 3. So what will happen to carrier, sorry, the current ripple, this will be 0 here, but it will rise and fall. So equal interval it would be and equal amplitude. So almost a triangle. And then it will continue 0 and then again it will have something triangular shape, very similar but inverted triangle. So peak to peak ripple is basically coming like this. This is only half peak, 0 to peak. Peak to peak meaning the positive peak to negative peak. This is the peak to peak value. So if asked like what is the peak to peak value, you have to tell from the positive peak to the negative peak and not just 0 to peak value. That is why this is highest, because in this subcycle it is going only on one direction. Another half cycle it is going only on one direction. Whereas any other case of MR if you take, and this I am talking about IR ripple, which is corresponding to MR, zero crossing. If you talk about IY ripple, that will correspond to MY, zero crossing. IB ripple will correspond to MB, zero crossing. Any other value of MR if you take, you see that these values are changing within this subcycle itself. It is going negative, then positive, then again coming back to 0. So it's having multiple transitions across 0. That's why the amplitude comes down. Here it is freely going to one very high value and coming back to 0. So which is why we see the worst ripple coming at the 0 crossing. These intervals may look little bit exaggerated. Depending on the values or modulation index, this may be little bit smaller. Correct? Fine?
Yes, sir.
Okay, so then I'll stop over here. Any doubts you may ask? And I now close this sine triangle PWM. If still you have any doubts, you can ask.